Hello, welcome to the incoming course, Classical Orbital Elements, Kepler's Equation and Baker's Equation by Dr. Ayenshola Ogundele. The description of the course is given as follows. Tycho Brahe, a pre-telescopic astronomer, widely known for his unprecedented accurate astronomical observations and credited with the launch of the scientific revolution, together with Johannes Kepler, laid the groundwork for Isaac Newton's greatest discoveries. Johannes Kepler tapped into Tycho Brahe's mechanical ingenuity and recordings of accurate data on the positions of the planets to unlock the secrets behind Tycho's observatory data. Aristotle's idea that the heavenly bodies exhibit circular motion was replaced during the scientific revolution era with the Kepler's ellipticity theory of the orbit of each planet, which was based on Tycho's accurate observations and data on the position of Mars. The concept of classical orbital elements, a set of 6 parameters that define an orbit around the central body, and known as Keplerian elements, are important for the prediction and understanding of the spacecraft and celestial bodies' motion. In the years 1601 and 1619, Johannes Kepler built upon Tycho Brahe's data to develop his 3 laws of planetary motion. Kepler's laws were mainly description of planetary motion. The scientific Renaissance era resulted in Isaac Newton's 1687 publication of Principia, which formulated the laws of motion and universal gravitation. The new course, Classical Orbital Elements, Kepler's Equation and Baker's Equation, describes and develops Keplerian orbital elements. Keplerian orbital elements, which describe the shape, size, and orientation of an orbit, the importance of radar stations in determining spacecraft and celestial bodies' orbital elements, and the Kepler's and Baker's equations, transcendental equations, are explained in the course. The course modules are as follows: Module 1, Module 2, Module 3, Module 4, Module 5, and Module 6. Each of the modules is as follows. Module 1, Radar stations and classical orbital elements. Module 2, Time-change periapsis and special case of circular orbit. Module 3, Kepler's equation for elliptical motion. Module 4, Baker's equation for parabolic motion. Module 5, Kepler's equation for hyperbolic motion. And Module 6, Exercises. Module 1, Radar stations and classical orbital elements. This module presents radar networks and stations and their uses for determining orbital elements, classical orbital elements, and determination of orbital elements from position and velocity vectors, and vice versa. Radar stations provide observational data important for determining celestial bodies and spacecraft orbital elements, thereby help to contribute to a better understanding of the space environment and enable essential tasks such as spacecraft mission planning, ephemeris prediction, orbit determination, collision avoidance, and a host of others. Module 2, Time-change periapsis and special case of circular orbit. In this module, time-change periapsis and its applications, development of time-change periapsis equation, and special case of circular orbit are described. The time-change periapsis is the elapsed time since an orbiting object last passed its periapsis, the point in its orbit where it is closest to the central body. Module 3, Kepler's equation for elliptical motion. This module presents elliptical orbit Kepler's equation, neutralizing Kepler's equation root finding method, and practical implication of the elliptical Kepler's equation. It is important for determining celestial bodies and spacecraft positions at any given time in their elliptical orbits around the central body, such as the Sun. Module 4. Baker's equation for parabolic motion. In this module, the Baker's equation and its importance are highlighted. It is a special form of Kepler's equation for parabolic orbits that relates the time elapsed from periapsis passage to the position of the orbiting body. Module 5. Kepler's equation for hyperbolic motion. This module presents Kepler's equation for the case of a hyperbolic trajectory, Newton's method for solving hyperbolical Kepler equation, and application of hyperbolic Kepler's equation. Module 6. Exercises. To comprehend the concepts of classical orbital elements, Kepler's equation and Baker's equation for elliptical orbit, parabola trajectory, and hyperbola trajectory, exercises are provided. Through various exercises, applications of the derived equations are explained in an easy-to-understand manner. The learning objectives of the incoming course, Classical Orbital Elements, Kepler's equation and Baker's equation, are as follows. Understanding of the importance of radar in determining classical orbital elements of a planet or spacecraft. Ability to determine orbital elements, given position and velocity vectors, and vice versa. Understanding of time, since periapsis and special case of circular orbit. And understanding of Kepler's and Baker's equations development and their importance. Thank you for your attention.